In section 2.6, we're going to discuss what are referred to as homogeneous equations or homogeneous differential equations. And there's another time where all of this section is referred to as substitutions and transformations. Substitutions and transformations. Now, on this one, we're going to be making a very specific substitution. If our equation can be written as dy over dx equals g, which has every place we have a variable, y over x, then this is going to be referred to as being homogeneous. If every place that our variable exists, it can be rewritten in a form where we have that expression, then we're going to be able to make a substitution. So first of all, we need to solve this for dy over dx. So let's move the dy to the other side, and that'll give us xy plus y squared plus x squared dx. On the other side, we have x squared dy. So if we move the dx over here, that'll give us dy over dx on the right, and we'll move the x squared to the other side. So the other side we have xy plus y squared plus x squared, all of that over x squared. Now, right now, we don't see the expression y over x everywhere. We see some y's and we see some x's intermingled, but let's take this fraction and simplify it. So let's take xy divided by y squared divided by x squared, and x squared divided by x squared. So that's equal to y. So notice that this x will reduce one of those. The x squareds will cancel, leaving 1, and nothing reduces in the middle. But we're going to be able to rewrite this in terms of y over x. Notice the first term is simply y over x. Now the second term is not just y over x, but it is y over x squared. If they're both squared, we can bring the exponent out and have y over x on the inside. So notice that each location that we have a variable, we actually have y over x. So we're going to make a substitution. In place of y over x, we're going to put v. So on the right side, we would have v plus v squared plus 1. Notice when we do that, we have 3 variables. We have dy, we have dx, and we have v. So let's see if we can relate dy over dx to v's. So let's isolate y here. So if we solve for y, we would get v times x equals y. And then if we take the derivative of this with respect to x, then we would get dv dx times x plus v equals dy dx. Now you might say, how do I get that left side? If we use the product rule, the derivative of the first times the second plus the first times the derivative of the second. Well, the derivative of x with respect to x is just 1. But the derivative of v with respect to x is dv dx. And I put plus here, that should be equal. So sometimes the way the book writes this is that right side of that is some function of v. We've replaced y over x with v, so the right side is a function of v. So we want to express the left side in terms of v and x. So dy dx is dv over dx times x plus v. So we're substituting in place of dy over dx, that expression. And the right side is, we could call that g of v So we could solve this generically, but typically instead of solving it generically, we want to solve it in terms of our transformation. So if we were doing it generically, then at this point we would subtract v from both sides. So those cancel. Let's see, we want to move the dx and the x to the other side. So that would be dx on top, x on bottom. On the left, so let's leave the dv, move g of v minus v to the other side. And then, depending on what our function is, we can integrate both sides, and we can get v and x and get rid of the dv and the dx. So this is generically what we would have for our specific problem. Let's see where we want to do this. Let's just go back to dv over dx times x plus v. That's the left side. The right side is v squared plus v plus 1. That's what we have on the right. Again, we replace dy over dx with dv dx times x plus v. So now this is going to be separable, so let's separate and integrate. So we're going to subtract v from both sides, so those cancel. That gives us dv over dx times x. On the right side, that gives us v squared plus 1. If we move the v's to the left, then we'll have v squared plus 1 on bottom, and we'll have dx over x on the other side. So now we integrate both sides. The right side, when we integrate dx over x, that's natural log absolute value of x plus c. The left side, that's just arctan of v. If we have du over u squared plus a squared, in this case a squared is 1, so a is 1. Then remember that's 1 over a arctan u over a, but a is 1. So we can solve this for v. If we take tangent of both sides, we would get that v is tangent of natural log absolute value of x plus c. Well, remember what v is. V is y over x. So if we multiply both sides by x, then y, and we would technically have to multiply that one also, y is x tangent of natural log absolute value of x plus c. So that's what we get when we make a substitution and then we solve it as a separable differential equation. So it does turn out that anytime we can make this substitution, in place of y over x, put a v. Now we can only do that if every place we have variables, we can rewrite it as y over x. If we have some y over x's and some y squareds over x to the first, or some y's over x's to a different power, if we cannot put it explicitly in this form, then it's not homogeneous and we can't make that substitution. But if we make that substitution, then since this is our relationship between v, y, and x, then when we isolate y and we differentiate both sides, then dy over dx is that. We replace dy over dx with that. We have our right side from replacing y over x with v. And then we separate and integrate. So let's do another example. Let's take a look at this one. Let's begin by getting dy over dx by itself. So I guess we could move the dy term to the other side. So that would give us x squared plus y squared dx equals minus 2xy dy. So if we want dy over dx That's going to go over there. That's going to go over there. So on the right side, we would have dy on top, dx on bottom. On the left side, we would have x squared plus y squared. And on bottom, minus 2xy. So since we have only one term on bottom, we're going to take each piece on top and divide by the denominator. And that equals dy over dx. So let's see. The x and one of those x's cancel here. This y and one of those y's cancel. We can factor a negative 1/2 out front. We have a 2 on bottom that's negative, so factor it out, and that's going to leave us x over y plus y over x equals dy over dx. Now you might say, hey, this is not homogeneous, but if we take the reciprocal of the first one, then this could be written in terms of y over x. So we could call this 1 over y over x. Remember that anytime you do 1 over something, it's the reciprocal of whatever that is on bottom. So 1 over y over x, this means the reciprocal of y over x, which is x over y. So if you keep, change, flip here to simplify this, you would get x over y. So since every place we have our variable, we have a y over x, then we can make our substitution. That in place of y over x, we can put a v. So we have 1 over v plus v. And then we want to replace dy over dx. And remember what we got when we did that. If y is v times x, then if we differentiate that, dy over dx is dv dx times x plus v, using the product rule. So the derivative of this times that plus this times the derivative of that. So in place of dy dx, put dv over dx times x plus v. So now we have our entire differential equation in terms of v and x. Again, our final answer needs to be x's and y's, but this is going to give us something that's going to be separable, and that once it's separable, we can integrate it, we can solve in terms of v and x, and then we can make our substitution. So let's move this v to the other side. So we have dv over dx times x on the right. And we might have benefited by not factoring out that 1. Before we factored that out, we would have had negative 1 over 2v minus v over 2, and now we're subtracting v. Say that again. If we would have just replaced y over x with v, and then distributed that negative 1/2, we would have had negative 1 over 2v, v times negative 1/2, or negative v over 2, and then we're subtracting v. So let's get a common denominator, which would be 2v. So if we get a common denominator of 2v, then on top we have a minus 1, a minus v squared, and a minus 2v squared. So minus v squared minus 2v squared, that's going to be a minus 3v squared. So that equals dv over dx times x. So if we separate and integrate, we would move the dx to the other side and divide by x. That will leave us dv on the right side. And if we divide both sides by this, we would end up with the reciprocal. We would end up with 2v over minus 1 minus 3v squared. So how are you going to do that? We could factor a negative out of the bottom, and let's put a 2 out front with it, that 2. So when we integrate both sides, that's going to leave us a v on top. If we take the negative out on bottom, that's going to leave us 1 plus 3v to the second on bottom. And if we take the 2 out front, that leaves us a v on top. And this is just going to be u and du. If we let the bottom be u, then du is 6v dv. So we have a v, a dv, so we need a 6 here, and we need to divide by 6 there. So after we make that correction, that's just going to be du over u, which integrates into natural log absolute value of u, which in this case is 1 plus 3v squared. On the other side, when we integrate, we end up with natural log absolute value of x plus c. Technically, it doesn't matter which side we put the plus c on or not. So we could do several things here. We could go ahead and substitute in at this point in place of v. Remember what v is. V is y over x. Or we could try to isolate v first and then make our substitution. So let's do that. Let's try to isolate v. So we're going to eventually want to make this natural log go away. So let's divide both sides by negative 1/3. Or if we're dividing by negative 1/3, that's the same thing as multiplying by the reciprocal. So that gives us negative 3 natural log absolute value of x plus c. On the right side, natural log absolute value of 1 plus 3v squared. Now, notice I didn't put a parenthesis here, and I did here. If we distribute this negative 3, we're going to have a negative 3 on the natural log and a negative 3 times c. Well, a constant times anything is itself. So to get this natural log to go away, we can do e to both sides. On the right side, we have e, and we have a natural log with no coefficient, so those cancel, leaving us 1 plus 3v squared. On the other side, we're not going to be able to really, we can do this a couple ways. We have a sum in our exponent, so we could rewrite this as e to the negative 3 natural log x times e to the c. This is a constant raised to a constant, so that's just a constant. If we get this exponent moved to the numerator, or the exponent, this coefficient moved to the exponent, then the e and the natural log would cancel, leaving us, and we're just going to do away with that with the absolute value here, x to the negative 3 on that side, 1 plus 3v squared on that side. So we could subtract 1 from both sides. We could divide both sides by 3. So k x to the negative 3 minus 1, all of that divided by 3, that's v squared. Square root of both sides, then we get v, technically plus or minus the square root of k x to the negative 3 minus 1, all of that over 3. Well, remember what v is. V is y over x. So if we want to get y by itself, we can multiply both sides by x, and we get that y is x times the square root of k x to the negative 3 minus 1 all over 3. So that's what we would get when we separated and integrated. So let's take a look at one more. Let's take a look at this one. Now the other two, when we isolated dy over dx, we had one term on bottom and we just divided each piece by that denominator. One term on bottom, so we divided each piece by that denominator. Well, if we have more than one term on bottom, that doesn't work. We can't just simply divide this by both of those, divide this by both of those, or let me say that if we were to do that, that's not really going to get us very far. And then we would have the same thing with the other term, because nothing there reduces. We could factor an x out on bottom, but that's still not going to really get us anywhere. So if we're trying to get a y over x, or we could have a y over x to a power, then if we look at the numerator, we've got y squareds and x squareds. So if we look at the y, if I have a y to the second on top, I need an x to the second underneath it to turn it into a y over x to a power. So let's see what happens when we do that. Let's multiply the top by 1 over x squared and the bottom by 1 over x squared. Whatever we multiply the top by, we have to do that on bottom. So that gives us dy over dx equals y squared over x squared, or we could call that y over x squared. When we distribute here, the x squareds cancel, leaving us minus 3. When we distribute here, this x will cancel one of those x's out on bottom, giving us y over x. And when we distribute here, that x squared will cancel with 2 of those, leaving us an x, y to the negative 1, or we could call that x over y. So every place we have either a y over x or an x over y. We rewrote this last time as 1 over y over x. Another way we could do this is if v is y over x, if we take the reciprocal of the right, we would have to take the reciprocal of the left. Well, the reciprocal of the right is x over y. The reciprocal of the left is 1 over v. We can make our substitution and call this dy over dx equals v squared minus 3 over v plus 1 over v. So now we have all of our y over x's substituted for. We also need to substitute for dy over dx. And remember what dy over dx is? Dy over dx is dv dx times x plus v. Just by oscillating this for y and doing the product rule. So we have dv over dx times x plus v equals, on the right side we have a complex fraction, so to make this v go away on bottom so our fraction is not complex, let's multiply the bottom and the top both by v. So that will give us v cubed minus 3v over v squared plus 1. Now that we have it in terms of v's and x's, let's separate and integrate. So we're going to subtract v from both sides. So those will cancel, giving us dv dx times x equals, let's see, we only want one term on the right side, so let's get a common denominator. Our common denominator will be v squared plus 1, so we're going to multiply top and bottom by v squared plus 1. So if we combine these, we have v squared plus 1 on bottom. On top, we have a v to the third minus 3v minus v to the third minus v. So v times v, that's v to the third, so minus v to the third minus v. So the v cubes cancel, and that's going to leave us a minus 4v on top, v squared not that. V squared plus 1 on bottom, dv over dx times x on the other side. So separate and integrate. Move the dx and the x to the other side, so that's going to give us dx on top, x on bottom. That's going to give us dv, and if we divide both sides by that, or if we multiply both sides by the reciprocal, that goes away, giving us v squared plus 1 over minus 4v on the other side. Integrate this. We've got our v's on one side, x's on the other, so we're going to get natural log absolute value of x plus c on the right. On the left side, we can pull the negative 4 out front on bottom. And we can divide each of those by v. So v squared over v, 1 over v, dv. V, that's going to be v to the 1 bigger power over that power. When we integrate this, this is just 1 over v dv, or dv over v, so that's natural log absolute value of v. So now we just, if we tried to solve this for v, this would be pretty challenging because we have a v on the inside of the log, a v on the outside. So instead of doing that, let's just replace v with y over x. So we have a minus 1/4 out front. V squared would be y squared over v squared. That's over 2, or we can put the 2 on bottom, plus natural log absolute value of y over x equals natural log absolute value of x plus c. So just like it was hard to solve the previous step for v, it would be hard to solve this for y. Several things we could do there to get it a little bit more isolated, but most likely this one is going to be implicit. X and y's mixed together. The whole point here is that if we could rewrite our differential equation where we have dy over dx on one side, then and every place we have a variable as y over x or x over y, then we can make the substitution that v is y over x. So that gets us a function of one variable on the right. And if we do that, then once we replace dy over dx, once we translate dy over dx to our new variable, then that's always going to give us something we can separate and integrate. Separate and integrate.